All right, in this video, we're going to learn about electrochemistry. So let's get started. This is a little bit of review from first semester general chemistry. What is the oxidation state of chromium in Cr2O7 2-? This is the dichromate ion. Can you tell and figure out what is the oxidation state? Might be good just to pause the video, make a guess. All right, hopefully you did a little bit more in guess and were able to calculate what it is. The oxidation state, this is how I would determine it. We know the overall charge is a -2, and we can assume that the oxygen has a -2 charge, and we can do a short calculation to figure out what it is for chromium. So I set it up this way. Since I have two chromiums, Cr2, I call it 2x, and then I'm going to add 7 times the -2 charge for the oxygen, and that equals the overall charge of -2. Then we can just set up a little formula, so it ends up being 2x minus 14 equals -2, 2x equals 12, and then divide by 2, x equals 6. The way I like to write that is actually to put the +6 above the chromium to indicate the charge of one of the chromium atoms. And then I would put a -2 above the oxygen to indicate that an oxygen atom in this ion here has a oxidation state of -2. So it's important to remember as we get into electrochemistry. There's some notes on the screen for my students. All right, we're going to cover chapter 17 in the Zoomdahl textbook on the Adam's first approach here. And we'll be looking at the following sections here throughout a series of talks coming up on chapter 17. Our goal for this chapter is learn how to describe how electrons move between atoms and how we can predict which reactions are spontaneous, which ones are not. How can we determine the voltage that goes along with these, and then what are the technologies that come out of this, and why is this important for chemists, for scientists, and for life itself. All right, so we'll have 4 key lectures on this, probably a few more here to get through all the topics in this chapter. Very exciting chapter because we get to deal with some very practical technology that's all around us. And one of those is electricity. How can we generate electric current, voltage, charge, all these things from electrochemicals? Part of this this experiment, well, part of this lecture here is to get ready for the experiment that our students are going to do for lab this week, specifically on this particular day. And they are going to make batteries using different metals, and in fact make a potato battery where they'll measure the voltage that comes out using different types of metals. And we're going to start getting ready for our homework dealing with some of the information here in chapter 17. Our goal is to learn about electrochemistry, which is really all about transferring electrons between atoms. When we're dealing with electricity, electric current, there's some key terms to keep track of. One of them is voltage, another one is amps, there's resistance, ohms, and all of these things work together to create power. So electricity is the free movement of electrons from one atom to the next, and it creates those terms that we like to see. This typically happens in metals, which behave kind of like a series of electrons with a sea of electrons, and these electrons can move freely throughout the material. If you can apply pressure, this electromotive force, it's called a volt. The amp is the rate at which the electrons are flowing through the material, and we'll be discussing that towards the end of this chapter. And ohm is the resistance to the flow. It's kind of like a pipe here, is shown in the picture, and the greater the pipe in diameter, the less resistance it's there. Smaller the pipe, more resistance. Electricity is often summarized with Ohm's law, which equals volts equals the amps, given the symbol I, times the resistance. We're not going to get into a lot of that. We're going to look at each component, how chemistry provides an understanding to power, to voltage, and to current. Now, one of the things that we want to get started with is to understand how do chemicals transfer electrons. And this can be done with a spontaneous chemical reaction that takes place between zinc and copper. So we're going to watch a little video here, and I'll narrate it here. So there's a zinc metal piece that's been inserted into a copper nitrate solution, 1 molar, very concentrated. You can see the blue colors of the copper. So what happens is there is a spontaneous chemical reaction that takes place between zinc and copper. The copper +2 ions are blue, but they are able to take the electrons from zinc, and then they get converted into copper metal, which is this brown liquid here, brown metal to the bottom. The zinc ions are created from the zinc metal, and so there's some electrons that are being transferred between copper and zinc. And so this electrochemical change that takes place is very important. One, it's spontaneous, and it takes place between the metal and the ions here that are in solutions. So we say that the copper metal actually plates out. Plating out means turns into a solid, and often is done on a surface of the other metal that's in there. Zinc metal actually gets turned into zinc ions, which are colorless in this particular experiment. So there are some useful chemical changes that take place because the electrons are transferring. But there's no useful electricity that's generated in this particular combination of solutions. But we do get to understand some of the basics that are taking place. Zinc metal, which is listed as zinc solid, gets converted into zinc ions as it releases, produces, gives off, transfers 2 electrons. We'll be using all of those words synonymously. Copper ions, because of the +2, they react, gain, obtain 2 electrons that come from the zinc. That's enough to reduce it to copper 0, which is copper metal, a solid, and that falls out of the solution. So these 2 reactions can be written together to summarize the chemical reaction that took place in that video between copper ions and zinc metal. That's a spontaneous chemical reaction. We're going to learn how that's spontaneous, why, and how we could predict that ahead of time. There's some key terms we need to understand with electrochemistry. In electrochemistry, we're dealing with oxidation and reduction of particular ions and solids like metals. And that is the transfer of electrons. So we have some key terms. There is an oxidation process that is taking place where loss of electrons is occurring from one chemical species. Another one is species in the system is gaining the electrons. That's called reduction. Now, some confusing terms, not meant to be, but it's the way the chemists refer to the things that we use. Reducing agent is our term for the element that's undergoing oxidation. It's causing reduction while it's being oxidized. The oxidizing agent is the material that is undergoing reduction, but it's causing something else to oxidize. I remember these terms by using the little phrase here, Leo roars grr. LEO means loss of electrons. Loss of electrons is oxidation, and grr, gain of electrons, is reduction. There's many other ways to remember this. This is the one I've chosen to remember. Now, electrochemistry is very interesting to show some spontaneous chemical reactions, but we really want to get at the heart of what makes a battery. This has been an important technology for humankind, is to generate electricity remotely and independently in these little objects we call batteries. Some of the key parts of a battery are a cathode, an anode, electrolytes, and there's some other parts to it too, in the direction the electrons are flowing and how you would hook it up to create useful electricity. So we want to look at these different parts as a chemist would, so we can see the different parts in more detail. So in order to create useful chemical energy, or actually electrical energy, the trick over the years and the key part of the technology was to actually separate the various parts of the chemical reaction that were taking place. What does that mean? Well, there was an oxidation process that's taking place and a reduction process. And how can you separate these into two different half cells, as they are referred to? If you can start to understand the different parts and the components and how to tweak and improve and optimize battery technology. Now, over the years, these spontaneous electrochemical cells have been given a number of different names. One of them is a galvanic or voltaic cell, after the last names of some famous scientists who developed this technology many, many years ago. And they just all mean the same thing, battery. They're all synonymous. We can say galvanic cell, we can say voltaic cell, we could say a battery, same thing, same thing, same thing. We're not even implying anything different. We're just saying there's just different ways to describe a battery. All right, some of the key terminology and parts as we separate them out to understand the chemistry that's taking place. There is in this particular example between zinc and zinc ions and copper ions, there is an oxidation process that will take place where the zinc metal and the zinc ions are. In fact, in this particular example, zinc is going to give off 2 electrons to convert into zinc ions, which are the chemical species that exist in aqueous solution. This is called oxidation, and this process will take place at a piece of metal called an anode. And this is given the negative charge in our system, just arbitrarily given that. These electrons that are generated from the oxidation process are given off through the wire, a metal wire, like copper wire, over to a piece of copper that's inserted into a copper solution. This copper solution has copper plus 2 ions in it. And these copper 2+ ions then gain the electrons from the zinc that's coming off, and the copper 2 ions get converted chemically into copper metal. This copper metal can stick to the copper metal that's already in there, thus increasing the size of the copper piece that's in there. This is referred to as reduction, and this is given the term cathode to name the piece of metal that's taking place. This is given the term positive to indicate the polarity of this side here. Now, the reason why this can generate useful electricity is from really a little trick that was developed over years called a salt bridge. There needs to be anions and cations that are able to freely transfer in between these two compartments to balance out the charges that are being created or taken away in both of the half cells. You'll find that electrochemists will try to simplify this whole notation, this whole description in a simple electrochemical notation, just shown on here on the screen with zinc solid, a bar meaning a change in phase between zinc solid and zinc ions, double bar for the salt bridge, and going over here to the reduction side, copper 2 ions aqueous, phase change, and giving off, turning into a copper solid. This whole thing is called a battery and is the subject of today's lab. Batteries can be made by inserting 2 metals of different types and connecting them with a wire, perhaps a voltmeter as shown here. There needs to be some kind of bridging between the 2 metal pieces so that the electrons can transfer through the wire and that a balance of charges can be maintained using electrolytes. As you can imagine, on the zinc side, what's happening is zinc metal is actually being eroded and creating zinc plus 2 charges. That builds up a positive set of charges in this solution. Then a negative anions or negative ions can, from the salt bridge, diffuse over into the anode side to balance out all the charges that are being created there. On the where did the zinc ions come from? They come from the metal. So the metal is actually disintegrating during this process. It's slow, but it can be seen and visualized over longer periods of time. Over on the cathode side, you can actually see the gain of copper metal that takes place as copper plus 2 ions get converted into copper solid, and they actually plate out and stick onto the surface of the metal piece, or they may fall down. But so as we lose the positive charges on the right hand side, cations will flow from the salt bridge into the copper solution to maintain a balance. That little trick with the electrolytes and the salt bridge is really what helps the battery to take place and close the circuit. Over time, you'll see that the zinc anode, where oxidation was taking place, that anode will decrease in mass. On the cathode side, it will increase in mass as copper is generated. So as the electrons move from the anode to the cathode, we see these chemical changes take place. These chemical changes take place are balanced by anions and cations moving through a salt bridge, which is basically a bunch of salt solution put inside. It could be a piece of paper or a tube that has the ability to diffuse in between there. We use the term electrodes to generically refer to the anode and the cathode. So these are very important to understand that it's really the metals that are transferring the electrons that are creating the voltage that's taking place, and the length of time that the battery will last really depends on the amount of metal you have in contact with the solution. Well, what generates and determines the voltage, as you see there, 1.1 volts in the system? Well, there are standard solutions that are made. 1 molar zinc and zinc metal is put into that, and copper metal put into a copper ion solution, let's say copper sulfate, copper nitrate, and it's 1 molar in concentration. This system has a potential or a voltage, an electromotive force that drives the electrons from one electrode to the next. This potential can be determined and calculated using a series of half reactions that we're going to go into detail in a little bit. So the cell voltage here is generated of 1.1 volts. How can we figure this out? Where did this come from? Well, in order to calculate the cell voltage, we're actually going to split this into 2 half reactions, an oxidation half and a reduction half. Once we recognize these 2 halves, we're going to be able to see that there are tables that tell us how much voltage is generated by each half reaction. And then we can add them together to figure out the overall cell voltage. This terminology is called E0 cell to give us the overall voltage. The voltage or potential that occurs at the oxidation step is E0 ox. That's how I refer it to. And E0 red is the reduction voltage part of the equation. So our job in electrochemistry is to determine what are these 2 half reactions. Who's being oxidized, who's being reduced, how many electrons are there, and what's the overall chemical reaction. How many electrons are being transferred? Well, hopefully you can see that zinc is giving off 2 and copper is receiving 2 in this particular example. All right, so in here, in our electrochemical cell, also known as a battery or galvanic cell, we see that zinc that's being oxidized and losing the electrons actually has a half cell voltage of 0.76 volts. One can look up on a table and determine the potential or voltage that's given off for the reduction side of copper. It's 0.34 volts. These are found in tables. These don't often have to be memorized. They just need to be looked up. So in this particular example, if we were to add those 2 reactions together, we would see this overall reaction of the reactants being copper ions and zinc solid. Those are the ones that are really reacting with each other, generating zinc ions and copper solid. We can add up the oxidation potential and the reduction potential to get the 1.10 volts that we saw on the voltmeters in these previous examples Yes, they were theoretical. All right. The use of these E naught values is very valuable because if we know what the value for oxidation and reduction, we can just look them up on a table. Just so you know, the tables are actually, for ease of purpose, listed always as a series of reduction potentials. Now, we needed zinc to be utilized as an oxidation potential. But so if we find something that needs to be oxidized, we're just going to need to know that it's reversed from what we experience. And if you reverse a chemical reaction, we're going to reverse the voltage. So you'll see a table of reduction potentials here on the next slide, and then also on the internet or PDF files can be found in our learning management system here. So here is a list of reduction potentials. You can see that it kind of gives a nice way to organize things based on voltage, and they're all set up in the same way. So some things like to be oxidized and some things like to be reduced, but you can see that these are all reductions because fluorine, the very first one on the top left, fluorine plus 2 electrons gives us 2 fluorides at a 2.87 volts. So here's a table that you can look up to find the reduction potentials for all sorts of ions and metals, liquids, solids, and gases. And so sometimes, though, if we're trying to figure out the oxidation potential, we may have to flip the chemical reaction. So down here is silver ions plus 1 electron gives us a 0.80 volts. Here's copper 1 plus an electron to give us copper solid 0.52. But we need to be careful because sometimes it's not just one type of ion, there may be different types. Because up here in the upper right, we see copper 2, which is actually more common, plus 2 electrons to give us the copper solid is 0.34 volts. So these are some important things to keep track of with our tables in understanding these half voltages. It's important to know our reference here, our middle one that's at 0, that's hydrogen ions. Like in an acid, that are 2 electrons are added to create hydrogen gas, and we'll speak more about that later on. All of these reactions are done at standard conditions for thermodynamic reactions, which means 25 degrees Celsius, 298 Kelvin, 1 molar for each of the aqueous solutions. If any gas was there, it's at one atmosphere of pressure. And so it's important to understand the signs of the voltages there, the potential, and if you flip them, you change the sign. In our lab, we're going to try to understand how to actually change the voltage outside of those standard conditions. And the way to do that is using the Nernst equation, where it tells us how to figure out the voltage of the actual voltage of a chemical reaction based on the standard potential that you would calculate minus 0.0257 volts divided by n, the number of electrons transferred, in the natural log of this Q. And so what are the different parts to this? So E, the thing all the way to the left, once again, is the potential you would read and determine on your voltmeter. E naught is what you would calculate under theoretical conditions. N is the number of electrons exchanged from the balanced chemical reactions. Ln is the natural log. And then Q is the equilibrium constant, not under equilibrium conditions, where we put the concentration of the product ions divided by the concentration of the reactant ions there. Now it turns out if you had 1 molar of each, then the natural log of Q would become the natural log of 1, which turns into 0. And then everything else, then the E cell becomes equal to E naught cell. So in general, if you have more reactants in these, you'll find that Q will be less than 1, and you'll end up actually, because of the sign change in there, the negative 0.0257, and then you'll get a negative term out of the log of Q, and that will give you voltages greater than you would get under standard conditions. If you change it so where you have more products, you end up with less. So these are important things to understand, and you can get those by thinking through the numbers that are there. So we're going to try to make batteries in lab with potato batteries. with different copper and zinc solutions and their various metals there. So it's important to understand what Q is, and that'll be explained more in lab. This Nernst equation, you can actually figure out some of the components of it by trying to take a series of concentrations and plotting them versus voltage. So Ecell, if we set that equal to Y, and we go get some voltages by changing Q, the concentration of the products divided by the reactants, we actually plot this. And by plotting that, hopefully you can see that, well, it might be better on the next slide. Well, we'll look at this one right here, that our Nernst equation actually looks a lot like Y equals mx plus b, where Y, there on the left-hand side, is the potential. And then mx, m is the slope, and that is of the 0.0257 divided by n. And ln of q is going to be our x. And then the cell, Ecell naught, is our y-intercept b. So whatever you get there for b, that's going to be pretty easy to find. What's a little bit harder to find is actually the slope and n and how to relate these two things together. So we're going to just do that for one of our last things here in this video. So let's say you got the following linear equation by fitting the data to a line, and a line equation is generated. Y equals negative 0.0123, x plus 1.006. The negative 0.0123 is related to the 0.0257 divided by n, and I already clicked and got the answer already. And so why is it 2 though? So how can we calculate the n is 2? Well, the slope is going to be equal to all of this negative 0.0257 divided by n from the Nernst equation. And that m is equal to negative 0.0123 from our linear equation. Now we just have to simply solve for n by multiplying both sides by n and dividing both sides by negative 0.0123. Our signs cancel out and we do the division, we get 2.08. Now this calculation is often rounded to the nearest whole number, which would be 2. And in this particular example, it does match up with the zinc copper oxidation reduction reaction that takes place. So there's some important things about the Nernst equation that we will look at a little bit more later on in the week as we get into electrochemistry, but we'll just kind of end it right there so you get a little bit of a taste for electrochemistry, some of the things that we'll think about, and it's really about understanding how electrons are transferred, this oxidation reduction reactions. Thanks for watching. I'm Dr. Ryan Hayes at Andrews University, Department of Chemistry and Biochemistry, and hopefully you learned a few things about electrochemistry in this talk. Thanks for joining me, and we'll see you next time.